What we're going to do today is finish on our coverage of capacity with some examples. And give another example about the signals from some of the past quizzes, and then move on to the next topic, perhaps if we get time, on transmission media. We went through Nyquist Capacity yesterday, and we talked about this concept of M, the number of levels. So I give one more example to explain that. And it's almost a repetition of the example that we used yesterday, but we'll go through it again. I have some data to transmit. 6 bits of data to transmit. I'm going to convert that digital data into a digital signal. And to do so, I'm going to apply some encoding scheme. The first scheme, if I want to transmit bit 1, I'm going to transmit at -5 volts. My digital signal, I'm going to transmit at different voltages, say +5 volts, -5 volts, for a period of time. So in my first scheme, where we use 2 levels, that is, in our equation, m equals 2, the simple or the obvious case. You just use a different level for a different bit. If I draw that, or draw the digital signal in this case, a bit more space. If this is +5 and this is -5, and I'm going to transmit 1 signal element per millisecond. Just for the example, that is, 1 level will last, we've transmitted for 1 millisecond, and then we'll change the next signalling element. So I want to transmit this 6 bits of data, 1, 0, 1, 0, 0, 0. I transmit a signal that represents the first bit. First bit is 1. Our scheme tells us to transmit for 1 millisecond at -5 volts. This is starting at time 0 after 1 millisecond of transmitting at -5 volts. Next bit 0 +5. 1 -5. 0 +5. So that's for 1 millisecond. The next 0 also at +5, so another 1 millisecond. And the last 0. That blue line is our digital signal using a particular encoding scheme, an example encoding scheme for this digital data, where we had 2 levels. We can define the signal or signalling rate. If we were sending 1 signal element per 1 millisecond, then we'd be sending 1,000 signal elements per second. If I send 1 in 1 millisecond, I can send 1,000 in a second. So we can define our signalling rate. SE, we've done this yesterday, it's just a different example. SE means signalling elements in this case. We're sending 1,000 signal elements per second. Each signal element, -5 represents 1 bit, +5 represents a bit. Each signal element represents 1 bit. 1,000 signal elements per second means 1,000 bits per second. That's our data rate with this scheme, sending at 1,000 bits per second. Let's use a different encoding scheme. Same 6 bits of data, but let's use an encoding scheme where we have where we represent 2 bits by 1 signal element. If we want to transmit the bits 0, 0, we're going to transmit it +5, 0, 1, plus 1.66 volts, 1, 0, minus 1.66, and 1, 1, minus 5. The reason for these 1.66 is that I just evenly divided this space of -5 to +5 into 4 levels. The difference between these two is 3.33, 3.33, and 3.33. That's just the reason for the values. The absolute values do not matter here. +5, +10, +0.1, that's not the point here. The point is that we use different levels. So this is our second encoding scheme, a different one. Here we have 4 levels. Let's draw our signal generated from our 6 bits of data. +5, 1.66, minus 1.66, minus 5. And in this case, we look at every 2 bits in our data. Remember, our data is 1, 0, 1, 0, 0, 0. We look at the first 2 bits of data we want to transmit, 1, 0. According to our scheme, to transmit the bits 1, 0, we send a signal pulse or a signal element at minus 1.66 volts. The next 2 bits, 1, 0, also minus 1.66. And the last 2 bits, 0, 0, at +5. That blue line is our digital signal representing this digital data. This is the duration of one signal element, 1 millisecond. 1 millisecond at minus 1.66, 1 millisecond at minus 1.66 for these 2 bits, and 1 millisecond at +5 for these last 2 bits. Signal rate, or signaling rate, is the same as before. We're sending one signal element every 1 millisecond. Nothing's changed there. It is 1 millisecond for each of those. 1,000 signal elements per second. Our data rate. Each signal element now represents 2 bits. If I'm sending 1,000 signal elements per second, then that means 2,000 bits per second. So this is illustrating that by changing the number of levels, we can change the data rate, keeping the signaling speed the same, keeping everything else the same. Just by changing the number of levels, m, we change the data rate. M equal to 2 in this example. We've ignored the bandwidth. With m equal to 2, we got a data rate of 1,000 bits per second. With a different scheme, with m equal to 4, we get a data rate of 2,000 bits per second. M equal to 8, we have 8 levels. Each level represents 3 bits. +5 maybe 0, 0, 0, and then we'd have 0, 0, 1. We'd have 8 different combinations. M equal to 8. What's our data rate? What would our data rate be if m equals 8? Can your computer calculate? What's the data rate if m equals 8? In the first case, m was 2, and we got 1,000 bits per second. In the second case, m equals 4, we got 2,000 bits per second. If m equals 8, what do you think we're going to get? All right, first, faster or slower or the same? That one is 1,000, this one's 2,000. M equals 2, M equals 4. Third one, M equal to 8. Someone help him. What's it going to be? If we increase M to 8 different levels. How many bits per signal element in that case? If we have 8 different levels, each level represents how many bits? If we have, his answer was 4,000, not correct. Anyone want to help him? 8 levels. How many bits per level? Come and do it on the board here. Come and write down the 8 different levels. Quick. Don't need your book. Just write down if you have 8 different levels. Here, what are the values in binary? If we had 4 levels, we had 0, 0. Okay, go for it. If we have 8 different levels, each level is going to represent 3 bits at a time. Good, well done. Thank you. Okay, so with 8 levels, that is m equal to 8, whatever the values are, plus 5, plus 4.5, doesn't matter what the voltage level is, but 8 different levels, each level can represent 3 bits. And if we were using this scheme, we'd send one signal element in 1 millisecond representing the first 3 bits. In our case, the first 3 bits are 1, 0, 1. So we'd send at this level 1, 0, 1. The next 3 bits are 0, 0, 0. So then we'd send at this level. So we'd send 2 signal elements. We're still sending one signal element every 1 millisecond. That is, our signal rate is the same, 1,000 signal elements per second, but each signal element represents 3 bits. 1,000 elements per second, 3 bits per element means 3,000 bits per second. So with this scheme, the data rate, 3,000 bits per second. Keeping everything the same, by increasing the number of levels, we increase our data rate. Where do we get the signal rate from? Well, I just simply specified 1 element per 1 millisecond, and I kept that constant for all 3 cases. The only thing that I changed is the number of levels. Or in general, we see the pattern log base 2 of m. This is 1 times the signal rate. Log base 2 of 2 is 1. 1 times the signaling rate is the data rate. In this case, m equals 4. Log in base 2 of 4 is 2. This data rate is 2 times the signaling rate. In this case, the signaling rate is still 1,000. M is 8. Log of 8 is 3. The data rate is 3 times the signaling rate, because we have 3 bits per signal element. This is where the log base 2 of m comes from in this equation. Here we were multiplying by the signalling rate. Where does the signal rate come from? Well, Nyquist determined that the maximum signal rate we can have is 2 times the bandwidth. So if we know the bandwidth of our signal, B, the maximum signal rate we can achieve is 2 times B. And if we know the number of levels, then the capacity, the maximum number of bits per second, is 2 times B log base 2 of M, the number of levels. So this is trying to illustrate how the number of levels impacts upon the data rate. Because we're dealing with binary, it makes sense to use a number of levels, a value of m, that when we take the logarithm of it, we get an integer value. If we use m equal to 10 levels, it doesn't really make sense, or it's inefficient, because what are the 10 levels? 0, 0, 0, 0, 0, 1. What is the 9th level? Well, we don't have another combination. We'd need to do something like 0, 0, 0, 0 as the 9th level, as the 10th level. But we'd have problems if we do this. So the value of m is typically a power of 2. 2, 4, 8, 16, 32 and so on, because we're dealing with binary. So we don't deal with that. We normally have a value of m which is a power of 2 in practice. So Nyquist capacity tells us increase the bandwidth will increase the signal rate, which increases the data rate. Bigger B, bigger C. But also increasing the signal levels, M, also increases the data rate. If you buy a channel or you buy a link which has a fixed bandwidth of 10 megahertz, according to this, the only way to increase your data rate is to increase M. But the larger B, the higher the cost it is. The larger M, the harder it is for the receiver to interpret what the signal is, or what the bits mean. Look at these two diagrams. Here we have between -5 and +5. There are just 2 different levels. What the receiver does is looks at the signal received. Okay, it measures it. Maybe with some errors it's -4.9 volts. And it says which one is it closest to, -5 or +5? Okay, it's close to -5, therefore it means this signal element, bit 1. In the second case, what the receiver does is measures the received signal strength and determines, okay, it's close to -1.66, therefore the bit must be, or the bits must be 10. Close to 1.66, -1.66, the bits must be 10. Close to +5, the bits must be 00. What the receiver does is takes the received signal, determines what the measured value is, compares it to what it's expecting to receive, and determines what the bits were. Now, if there are some errors or some noise, what is received is not this perfect straight line, but maybe something like this. If there's some noise in the system. So we measure the value, okay, it's -2. Which one is it closest to? Okay, this one, bits 01. Measure here, -1.3. Which one is it closest to? It's closest to -1.66, okay, 01. Measure here, because of this large amount of noise, measures, it's +1.6. Which one is it closest to? Here, the bits received, the receiver thinks, would be 01. That would be an error. We'd get 10, 10, 01, when in fact what was transmitted was 00, because of this noise. If we had the same amount of noise, in this case, it was somewhere around here, we'd measure the level. Okay, it's plus 3. Which one is it closest to? If we get the measured value of plus 3, it's still close to plus 5. We'd still get the correct bit, even with this large amount of noise. So the point is, the more levels we have, the more chance that we'll get bit errors because of noise. Imagine we have 8 levels divided between here. 1, 2, 3, 4, 5, 6, 7, 8 up here. A small amount of noise could cause an error. So that's where we cannot, in practice, increase the signal levels to an infinite value, because the more signal levels, the larger the impact of noise and the more bit errors that will occur. It's just that the Nyquist equation doesn't include noise. It assumes there's no noise. The Shannon capacity assumes that there is noise and calculates if there is some signal strength received, and we know how much noise, then we know the signal to noise ratio, and calculates the capacity based upon that. The bandwidth times log base 2 of 1 plus the signal to noise ratio. Let's do an example. First example. Let's take it over here. Make it easier for me to calculate. Let's say we have a communications channel. It has a bandwidth of 10 megahertz. So we have a link, bandwidth 10 megahertz. That's fixed. We send our signal across it, and we do some measurements. And what we measure is that the signal power received is 150 milliwatts. Now we're measuring the signal strength in watts, or milliwatts here. Remember, watts are proportional to voltage if we keep things constant. And the amount of noise that we measure, if we can measure the noise in the system, is 10 milliwatts. That's like saying that, okay, when I'm talking, and if you can measure the strength of the signal at your ears, it's at a level of 150. And if you can measure the noise caused by the air conditioners and everyone else talking and moving, is at a level of 10. So simply the signal to noise ratio is 150 milliwatts divided by 10 milliwatts. The units, of course, cancel out. It's a unitless value, is 15. The signal to noise ratio in this example is 15. The signal strength is 15 times larger than the noise. According to the Shannon capacity, the fastest we can send bits is the bandwidth, 10 million, 10 megahertz, 10 by 10 to the power of 6, times by the log in base 2 of 1 plus the signal to noise ratio. 1 plus 15. 1 plus 15 is 16. Log in base 2 of 16 is 4. 2 to the power of 4 is 16. So log in base 2 of 16 is 4. So our answer 4 times 10 times 1 million is 40 megabits per second. So with our channel with a bandwidth of 10 megahertz, we can send at 40 megabits per second under those conditions. That's when our signal was much higher than our noise. As you know, if the noise increases but the signal strength stays the same, the noise goes up, it's much harder for the receiver to successfully receive data. If I'm talking and everyone else starts talking, then it will be harder for people to listen to understand what's being said. If we increase the noise power, if another case, if the noise power doubled, that is, there was more noise in the system, from 10 milliwatts up to 20 milliwatts. Everything else the same. SNR is 150 divided by 20, which is what, 7.5? 150 divided by 20 is the SNR. And therefore our capacity is 10 million log base 2 of 1 plus 7.5, which is 8.5. What's the log of 8.5? 3 point something. You need your calculator to get the right answer. But we know the log of 8 is 3. So it's approximately 30 megabits per second. It's a bit more. The Shannon capacity formula tells us, under these conditions with a bandwidth of 10 megahertz and a signal power of 150 milliwatts, if we increase the noise from 10 up to 20 milliwatts, then we're going to decrease the maximum speed we can send data from 40 down to 30 megabits per second. More noise, the lower the speed you can send. And that's a theoretical limit of how fast we can send under those conditions. In practice, you're going to get less than that because there's other imperfections. We can think of the Nyquist capacity as the upper limit at the speed at which you can send if there's no noise. In real life, there is noise. The Shannon capacity gives us a more accurate picture of the upper limit. It's less than the Nyquist capacity. In practice, because of other imperfections, you cannot quite achieve the Shannon capacity. Some systems can get close, but you'll never go above it. If someone tries to sell you a product, a communications link, and they say the bandwidth is 10 megahertz, and they say this is what the SNR is, then you can determine what the maximum data rate is. If they say, under these conditions, the maximum data rate we achieve with our product is 50 megabits per second, you can say, no, you're lying, because you cannot go above the Shannon capacity. So these two formulas give us some approximation, or gives us some limits to which we can send, the speed at which we can send in practice. When you buy a product, at least you can evaluate whether you're close to capacity or not. Before we go through another example, we can see from the equation, increase B, the bandwidth, increases the data rate. Increase the signal power, here, increases the SNR, increases the data rate. Increase our signal strength, and we'll get faster. Or the capacity, the maximum we can achieve is higher. Increase the noise, like we just did, decreases the data rate. That's related to the SNR. Some other things which are not shown by the equation, if you increase the bandwidth, you may allow more noise into the system. Make B bigger, sometimes it will make the noise bigger, and therefore we have some trade-off to deal with. Increasing the bandwidth doesn't necessarily increase the data rate as much as we want, because noise gets larger in practice. Also in practice, if we make the signal power very large, we can cause other intermodulation noise. And it can be overload the receiver circuitry as well. So in practice, we cannot increase these to as high as we want. We have some practical limitations which limit our data rate. Any questions on these two formulations of data rate related to bandwidth? Two variations, they operate under different conditions. Of course, sometimes we don't know these values. If we don't know, then maybe we can just use the Nyquist capacity to give us another value or approximation of our capacity. If we know the signal-to-noise ratio, this is a more accurate value. But if we don't know it, we just know B and we know M, but not the signal-to-noise ratio, then we can use the Nyquist capacity, the previous one. So you should be able to, I think I even asked you to remember those equations in the exam. I can't remember, I have to check from last year, but they're not too hard. But understand where to use them as well. If I give a question and I give you the signal power and the noise power and the bandwidth, you should recognize, okay, I need to use the Shannon capacity formula to calculate the data rate. Or if I give you the data rate and the signal-to-noise ratio, and I ask what is the bandwidth, then you can calculate that as well. Another example which combines the two together. Have a read. Think about how we would solve that in the quiz. If there was a quiz next week and asked that question, what would you do? So we have a communications channel. It has some spectrum defined. So the channel uses frequencies between 3 megahertz at the minimum and 4 megahertz at the maximum. That's the spectrum. Has some signal-to-noise ratio. How many signal levels are required to achieve Shannon capacity? Let's write down what we know. From spectrum, what do we know that's going to be useful? Bandwidth. What's the bandwidth? 4 minus 3 megahertz. Spectrum goes from 3 up until 4. The bandwidth is just the width of that spectrum, 1 megahertz. So B, the bandwidth, we now know is 1 megahertz. So our channel, our length, supports frequencies from 3 up to 4 megahertz. That is a width of 1 megahertz. We have this SNR value. Note there's some units there, 24 dB, decibels. And we know our equations. The Shannon capacity, CS, B, log base 2, 1 plus SNR. Note the question is not asking about what is the capacity. It does not ask for the data rate. it asks for the number of levels. So you need to connect this. It says something about Shannon capacity. We would need this equation. It also says something about the number of levels. Shannon capacity doesn't consider the number of levels. The Nyquist capacity does. 2b log 2 of m. That's what we know at this stage in this question. What do we want to find? M. That's useless. That's our value that we'd like to find. M is the unknown. The number of levels. M represents the number of levels in our signalling scheme. What do we know? B. We don't know M. SNR. Be careful though. Here's the first trick in this question. The SNR used in this equation is an absolute value. We saw it's one power level divided by another. An absolute 150 divided by 10, absolute value of 15. Decibels is a different way to represent some ratio between two power levels. So this SNR is not exactly 24. We need to convert decibels to the absolute value of SNR. I'll show you how to do that in a moment. That's what we'll do. And then we will have this value. Once we do this conversion, we'll have SNR, we'll have B. We can calculate CS, the capacity. That is, we'll know the capacity, we'll know the bandwidth, we can find M. That's going to be our steps. To do this, we need to know something about decibels. And even for the next topic and later topics, we need to understand decibels. So let's skip, or let's move to another handout which talks about decibels. In your handouts towards the front somewhere, there's some document on definitions and concepts. And if you find that and scroll to the end, there's some information about units and prefixes, which we already know. If not, you'll read that tonight. There's some information on logarithms. This is high school mathematics. Refresh yourself because it's useful when we're dealing with decibels and other calculations. And there's some information on what are decibels. And I think you may have covered this in other courses, even in high school. So we'll go through it quickly, just with enough information for what we need. In any transmission system, we transmit a signal at some strength. The signal propagates across our link and it attenuates. It gets weaker over distance. And what's received is going to be less than what was transmitted. So we have some transmitted signal with some strength and a received signal, which is less than that. So there's some loss of signal strength. We need to measure, we use decibels as a way to measure how much loss. And in some systems we try to compensate by amplifying. Our audio amplifier takes my normal voice signal and increases it. So that causes some gain in the signal strength. So we have these two items of loss and gain. They're the inverse of each other. Decibels are commonly used to express, there's a spelling mistake, I'm sure there's many through here, express gains and losses. It's commonly used to express what is the a gain of some system. If we have an amplifier, we have some input power and it produces some output power. The increase or the gain is normally expressed in decibels. And this is how we calculate the value of gain in decibels. It's the ratio of two power levels. Here's our system, whether it's an audio system, a communication system, some system which takes some input power level, power in, and produces some output power level. An amplifier will increase. The gain of that system, expressed in decibels, is the ratio of the output to the input log in base 10 and multiplied by 10. If this is an amplifier and it takes a 1 watt input and amplifies our signal and produces 10 watts on output, then the output divided by input, the absolute gain, we could say, is 10. Why? Start with 1 watt, end up with 10 watts. We've multiplied by a factor of 10. That's the absolute gain of that system. It increases by a factor of 10. Measured in decibels, the gain is 10 divided by 1. Take the logarithm of that in base 10. The log of 10 in base 10 is 1. Multiply everything by 10. The gain in dB is 10 decibels. With an absolute gain, a multiplier of 10, our gain in decibels is 10 decibels. This is a unitless value. This has a unit of decibels, or a prefix of decibels. Let's say our amplifier takes 1 watt as input and produces 100 watts on output. Then our absolute gain is now 100. We increase by a factor of 100. Our gain in dB is 100, or 100 divided by 1, which is 100 here. Logarithm of 100 is 2 times by 10, 20 dB. So the absolute value and the value in decibels are the same, just using different units. And using decibels is very common in communication systems. So that's how to calculate the gain in decibels. We take the output power divided by the input. This can be an amplifier, but in a communication system, I'm going to use the same diagram, some communications channel, a link, for example. We have some input power at the transmitter, say 1 watt. I transmit with a power level of 1 watt. But we lose power over the channel, remember. Our signal attenuates, it gets weaker. So the power level at the receiver is going to be less. Let's say it's 0.01 watts. The power level at the receiver is less than at the transmitter in our communication system. Perform the same calculations. We can say the absolute gain is this divided by this, which is 0.01. The gain in decibels, using the same equation, 0.01, take the logarithm. What do we get? What's the log in base 10 of 0.01? Use your calculator if you wish. Shouldn't need it. What's the log of 0.01? Negative 2. Good. The log of 0.01 is minus 2. Multiply everything by 10 and our gain is minus 20 dB. Why is it? Well, we know 10 to the power of minus 2 equals 0.01. 0.01, the logarithm equals minus 2. Multiply by 10, our gain of this communication channel is minus 20 dB. The minus means that we've decreased. So in fact, we could say the loss of that channel, how much power do we lose, is 20 dB. If we have a gain of minus 20 dB, then the loss is plus 20 dB, the inverse of each other. Or the other way, we could say the absolute loss is a factor of 100. Our received power is 100 times weaker than the transmitted power. So gain is either minus 20 dB, minus, if it's minus decibels, then the loss will be positive. That's decibels, so that's how we use them and calculate them. Used to express in communication systems gain and more commonly loss, because usually we lose power. So, given that, we have, coming back to our original question, we had SNR expressed in decibels. The Shannon Capacity equation uses SNR in the absolute value. You need to remember that. You cannot put a decibel value in this equation. It will not work. It will give you the wrong answer. You need to convert it to the absolute value. If we have 24 dB, what's the absolute value? It's equivalent to, how are you going to calculate it? We have 24 dB. We want to know this value. SNR is signal to noise ratio. It's a ratio of 2 power levels. So now we have 24 dB equals 10 log in base 10 of our SNR absolute value. SNR is the ratio of 2 power levels, power out, power in. So if this is the SNR expressed in decibels, we can find the SNR in the absolute value by solving this equation. 24 equals 10 log 10 SNR, which means 2.4 equals log 10 SNR. Why 2.4? Just bring the 10 to the other side. Divided by 10, divided by 10. Therefore, SNR equals 10 to the power of 2.4. If 2.4 equals a log of SNR, the inverse of the logarithm is the exponential to the base 10. SNR equals 10 to the power of 2.4, which equals whatever it equals, 250 something, approximately. I think 250, I've got the answer somewhere. Yeah, 251. So, make sure you understand decibels. that they are used to express a ratio or a ratio between two power levels in a logarithmic manner. We take the log and multiply by 10. Understand the concept of gain and loss. This gives us, this power out divided by power in gives us the gain of a system. The loss is the inverse. And we've used that to convert our signal-to-noise ratio given in decibels to the absolute value which is needed for the Shannon capacity formula. And all I did was take 24 dB. 24 dB equals 10 log our ratio of two powers, S, signal, divided by noise. Signal to noise ratio means signal divided by noise. It's a ratio of those two power levels. So SNR, or 24 equals 10 log SNR. Solve that for SNR gives us 251, approximately 10 to the power of 2.4. Any questions so far? We still need to solve our problem of how many levels. So from this point on, I'll assume that you can do calculations, you can do conversions between decibels and the absolute value. And when we cover the next topic, we'll see that decibels are used quite commonly in communication systems. So you need to be able to convert between the absolute value and the decibel value. Coming back to our problem was, what is M? How many levels do we need? Given this bandwidth, this SNR, how many levels do we need to achieve the Shannon capacity? Well, first, what is the Shannon capacity in this condition? We know B is 1 megahertz. We now know SNR is 251. So we can solve the Shannon capacity formula. Says the bandwidth log 1 plus SNR. Our bandwidth is 1 megahertz, 1 by 10 to the 6, times log in base 2. And another thing you need to be careful with, both of these capacity equations, sorry, not here, both the Shannon and Nyquist capacity use log in base 2. In decibel, we're talking about log in base 10. Don't confuse them. If you see log with no base, that is, if nothing is given here, then you assume base 10. Okay. 10 or 1 megahertz, 1 million, times log base 2 of 1 plus our calculated SNR, 251. We cannot put the dB value in this equation. That's why we needed to convert, which is 252. What's the log of 252 in base 2? Again, you need your calculator. It's about 8. Log great calculator, we don't have log in base 2. We'll come back to that. How do you calculate log in base 2 if your calculator doesn't have it? This is also in the lecture note, in the other handout. you can convert (251). My calculator's the other way. (7.97). It's about 8. Why? Log of 256 would be 8. Because 2 to the power of 8 equals 256. Therefore, 2 to the power of something slightly less than 8, 7.9, is going to be 252. Or we can calculate more precisely. It's actually 7.97. So, yeah, we're here. Separate this. Let's approximate the value to 8. The answer of this is 8. 8 times 1 times 1 million is 8 million. Approximately. 7.97 megabits per second. So, what we know so far in our communications channel with a bandwidth of 1 megahertz, with an SNR of 24 dB, the maximum speed we can send is 8 megabits per second. If we want to send 8 megabits per second, go back to our question, if we want to achieve this capacity of 8 megabits per second, how many signal levels do we need? Now we use Nyquist equation. We know the capacity we want, 8 megabits per second. We know the bandwidth we have, 1 megahertz. How many signal levels do we need to achieve that capacity with that bandwidth? So now, using Nyquist equation, 8 megabits per second is the capacity that we want. The bandwidth B is 1 megahertz. 2 times the bandwidth. This is the Nyquist equation. Log base 2 of m. In other words, 8 by 10 to the 6 equals 2 by 10 to the 6 log base 2 of m. If we want to achieve this data rate of 8 megabits per second, according to the Nyquist equation, if we have a bandwidth of 1 megahertz, we need m levels of our signal. Solve for m. 8 equals 2 times log in base 2 of m. Or keep going. 8 times 10 to the power of 6 divided by 2 by 10 to the power of 6 is 4. I just bring this to the other side. So 4 equals log base 2 of m. Therefore, m equals 16. Good. 2 to the power of 4 equals 16. If we have 16 different levels, one level represents 4 bits. The next level a different, so 0, 0, 0, 0. The next level 0, 0, 0, 1, and so on down to 1, 1, 1, 1. 16 different levels, each level representing 4 bits. that is m equals 16, if we have a bandwidth of 1 megahertz and 16 levels, we can achieve 8 megabits per second data rate, according to the Nyquist equation. And the data rate we want to achieve is 8 megabits per second. We want to achieve the Shannon capacity, which is calculated from the bandwidth and the signal-to-noise ratio. So this is an example that combines the two together to get some practical value. It tells us if I have my 1 megahertz channel and an SNR of 24 dB, it tells me the minimum number of levels you need is 16 in your signal. You need to design a signal encoding scheme with 16 levels. If you have less, if you had 8, if we had 8 here, then we'd get log base 2 of 8 gives us 3, times 2 would give us 6 megabits per second, which is not enough. We want to get 8 megabits per second. So it just brings the two together to get some practical or some limit in terms of the number of levels that we need. I think the trick is with both of these equations is to look at the information provided in the question. We were provided spectrum, which you need to be able to determine you can get bandwidth. We were provided signal-to-noise ratio. The hint immediately, I need to use Shannon capacity to calculate something. But then the question asks, we want signal levels. Then the next hint then is, I'm going to also need to use Nyquist capacity to calculate M, the signal levels. And then it's just a matter of solving, giving the information you have. Any questions on that? It's gone through some examples of those two capacities in some detail. We'll go through one more example today. I think when's the next quiz? Must be soon. Probably next week. Let's go through a different example going back to where? So we've covered that topic now, but we'll just go through one more example to finish the day. So in summary, we've looked at how signals are made up last week. Combine sinusoids together and we get any communication signal. We went through some calculations of data rate. We've mentioned that data can be analog and digital, or analog or digital. Signals can be analog or digital. In any communication system there are impairments, there's noise, there's attenuation, the signal gets weaker. We need to deal with them. And we've gone through two different formulations that give us, under certain conditions, how fast we can send in a particular channel. Before moving on to the next topic, we'll go through an example from some of the previous quizzes, if I can find them. Let me find the examples. Here's a question from one of the quizzes last year. And you can quickly try and answer it. Draw a plot of the following signal in the frequency domain. So now we're going back to what we covered last week about how signals are created, the relationship between spectrum, bandwidth, and eventually data rate. So we have a signal expressed as an equation. Zoom in. You need to draw a plot of it. That's the equation. That's all you need for this part. 10 sine 60 pi t plus 5 sine 120 pi t plus 2 sine 200 pi t. And the second part is, what you should be able to answer from this is, what is the spectrum of that signal? Draw a plot of the spectrum. What is the absolute bandwidth of the signal? Try and calculate them and draw the plot. If you're to draw the plot, you need to identify the components and their frequencies. 3 components, each have a particular frequency. What are they? I can see some people have drawn some axes. Some people have written the question down. I want to see answers. Write down . If I asked you to draw a plot of this signal in the time domain, you would need to use your calculator, you'd need to use some plotting graph or a computer to plot it. It's not so easy. But in the frequency domain, you need to identify the frequencies of each of the 3 components. We have 1, 2, 3 components, sinusoid components. First, you'll need to remember the general form of each component is the peak amplitude A sine 2 pi ft plus phase. Well done. There's no phase in these cases, but that's the general form. We see the phase is 0. Let's forget about the phase. We can see the amplitude of each component, 10, 5 and 2, the peak amplitude. And we can see from here 2 pi ft is equal to 60 pi for the first component. 2 pi ft is equivalent to 60 pi t. The pi's cancel out and the t's. 2f equals 60. It means f equals 30 hertz. For the first component, in this form, 2 pi ft, we've got 60 pi t, therefore f of this component must be 30. The frequency of the first component is 30 hertz. All I did is equated this to this and found f. frequency of the first component, the frequency of the second component, same approach. 120 pi equals 2 pi f. F equals 60. And the last case, f equals 100 hertz. So we can identify the frequency of the individual components just by knowing this general form and equating it to the given form. Note these three components. Each of them are multiples of 30 hertz. This is 1 times 30, this is 2 times 30, this is not 2. I'm wrong. This one's correct. It's not a multiple. That's wrong. To have a fundamental frequency of 30, they need to be multiples of 30. In this case, it's not. That is, this is not a multiple of this, and therefore we cannot directly determine the fundamental frequency of that signal. That's a case we cannot. So what can we determine? We can plot this. We plot frequency in hertz against the peak amplitude. So we just simply draw an impulse for each of those components. First component, amplitude of 10, frequency of 30. Second component, frequency of 60, amplitude of 5. Third component, frequency of 100, amplitude of 2. That's 2. That's the plot of our signal in the frequency domain. Of course, drawing a plot of that signal in the time domain is more complex. You need to plug in values for t. That's harder, but easy in the frequency domain. If you know the components and their frequencies, and you know their peak amplitudes, it's just a set of impulses at each frequency with the corresponding peak amplitude. Looking at this, the spectrum of this signal, well, it contains three components with 30, 60, and 100 hertz. This immediately shows us our spectrum, the range of frequencies included in the signal. And the bandwidth is easy. Look at the plot. It's the width from the minimum frequency to the maximum. This signal uses frequencies from 30 hertz up to 100 hertz, a width of 70 hertz. So we say that this signal has a bandwidth of 70 hertz. B, 70 hertz. 100 minus 30. And that would solve the question. I think there were two parts to solve that. So just relating those basic concepts between the signal equation, the plot, and the bandwidth. I think this question we've done on the board, or close to. We have another one. Let's try a different quiz then. One more question. The top question. Here's another signal. Quickly, 10 times 1 million. We can work out the frequency of this component 10 times 1 million pi t, we can find f is simply 10 times 1 million divided by 2, is 5 megahertz. This is 10 million times pi is equivalent to 2 pi f, therefore f is 5 megahertz for this component. And this would be 15 megahertz, and this 25 megahertz. So we could do the same. So we have 3 components with frequencies of 5, 15, and 25 megahertz. Why megahertz? Because we have this 10 to the power of 6 here. 5 because it's 10 divided by 2. It's 2 pi f. 30 divided by 2. 50 divided by 2. 5 megahertz, 15, and 25 megahertz. In this case, they are all a multiple of 5. 1 times 5 megahertz, 5 times 5 megahertz, sorry, 3 times 5 megahertz is 15 megahertz. 5 times 5 megahertz is 25 megahertz. In this case, the components all have frequencies multiple of one of them, 5 megahertz. So we immediately know the frequency of the resulting signal with all 3 components is that fundamental frequency of 5 megahertz. The frequency of S of t is 5 megahertz because the 3 components are all multiples of 5, integer multiples of 5. First question, what is the period? Well, period is the inverse of the frequency. If the signal has frequency 5 megahertz, 5 million, the period is 1 divided by 5 million. So that would be the answer there, which is what? 0.2 microseconds is the period. That's the time for one waveform, one cycle. Absolute bandwidth, same as before. It's the maximum frequency minus the minimum, which we had 25 minus 5. The bandwidth of this signal is 20 megahertz. It occupies a portion of the spectrum ranging for 20 megahertz. So you should be able to solve those questions in a quiz. Just quick questions about the components, the frequencies of components by equating to this 2 pi f general form, knowing how to draw the plot, determining the bandwidth, which is just the maximum frequency minus the minimum, and of course things like the period. And importantly here we had a fundamental frequency. Because the 3 components were all a multiple of 5 megahertz, the resulting signal has a frequency of 5 megahertz. Therefore a period is the inverse of 5 megahertz. In your own time you can look at other questions in that quiz. There's another one there on Nyquist and Shannon, but we've gone through a couple of examples. That finishes for today. Next week we'll move on to the next topic of transmission media. Things like what are the types of cables, copper, coaxial, optical fibre, and how does wireless transmission work. And we'll talk more about attenuation, decibels and so on. So make sure you understand decibels, and for the quiz, the next quiz, understand some of these things we've just gone through with Nyquist, Shannon, and these relationships of signals, bandwidth and so on. Let's continue next week.